Hey guys, so we're going to try a couple practice problems here about, these are actually open and closed tubes. Now remember, open tubes and strings are the same. So when I do the open tube one, it's the same deal as for a string. So this is an open tube, it's open at both ends. And so how do you approach these? I think, there's a number of problems on Quest that have pictures that look like this. And so you can apply this to Quest. Be careful when you work those Quest problems. Some of you are going to have open tubes, and some of you are going to have closed tubes for the same problem. So when you're talking to your friend and you're trying to do the same thing, exactly the same thing that they're doing, it may not work because your friend may have a closed tube and you don't. So here we go. This is an open tube. First thing that you can do is figure out how many total loops. And to do this, you can just count. A different color. Ah! So here's 1, 2, 3, 4, 5, and then there's this half and this half, which make a total of 6 loops. Which means this is the 6th harmonic. Okay? So, that's how you can start. Now, the next question you can ask yourself is how many waves are there? Now remember, a wave is every 2 loops, right? So if we have 6 total loops, and we divide by 2, because every 2 is a wave, that means there are 3 waves. Okay? Okay. So there you go. Now you may need to find out what the wavelength is. That would be lambda. So to find the wavelength, okay, you take your length, which total length of the tube is 48. So you can take your length of the whole tube, which is 48. And divide by how many waves there are. Well, we just found that there were 3 waves. 48 divided by 3, 16. And that's centimeters. So your wavelength is 16 centimeters. No problem. Okay. So that's lambda. Okay. Now, you may have to find the frequency. I'm going to change colors here. What is the frequency of these waves? There's an equation that we're going to need, and if you've been doing the Canvas module, you already know it. The equation, let me move this baby over. V equals F lambda. That's the velocity of a wave. So, the velocity of a wave is a function of 2 things. The frequency, how frequent the waves are, and the wavelength, how big the waves are. So here we have the wavelength, and let's say we want to find the frequency. We divide by lambda. Frequency is velocity divided by lambda. Now, the velocity of the wave. You're probably going to know what this is. All waves moving through the same stuff have the same velocity. That's why there is such a thing as speed of sound, because sound waves are waves, and they travel through air. So, all sounds that you hear are moving at the same speed right now. So, chances are the problem probably tells you what the speed of sound in air is. And there's a reason for that, because all these waves in this tube are all moving at the same speed because they're probably sound waves. So most of the time, speed of sound is around 340 meters per second. A lot of times, Quest will use 343. So, V, sound, is 343 meters per second. So for the frequency, we're going to take 343 meters per second and divide by our lambda. Now it needs to be in meters, so we're going to divide by 0.16. And you get some gigantic number, 2,000 something, 2,100 hertz, thereabouts. Okay, that's your frequency. Whew. Now, if you want the fundamental, because obviously that's not your fundamental. The fundamental, if you guys remember, is just one giant loop, right? So to get your fundamental, you would take that frequency, 2100, and divide by 6. Because this is the 6th harmonic. And whatever you get is around 350. That is your fundamental. So that's how you would use this knowledge. That's how you'd work one of these open tube problems or a wave on a string. I will say this, for waves on a string, all the waves traveling in a single string, they all have the same speed too. That's why most string instruments have different strings, because those waves all need to move at different speeds. And then there are other reasons there too. Okay, now I'm going to pause this and we're going to try a closed tube. Hey, I'm back. So here's a closed tube. So here we go. Closed tube's a little bit different. Closed at one end, open at the other end. Notice the pattern. When you're closed, you have a node. When you're open, you have an antinode. All right, how many loops we got here? Just count. 1, 2, 3, 4 and a half. So we have 4.5 loops. Pretty easy. Now, how many waves would that be? Well, a wave is every 2, right? So if you take 4.5 and divide by 2, what do you get? You get 2 1/4. Two and a fourth, or 2.25. Why is that? Well, because this is one wave here. There's one wave. Here's the second wave. 1, 2, and then you have a little quarter. Every wave is two full loops. So we have 2 1/4 waves. All right, what's our wavelength? Well, take your total length of the tube, divide by how many waves you have, which is 2 1/4 or 2.25. 45 divided by 2.25 is around, it's about 20 centimeters. That's our lambda. Okay. Now, let's see. We can do this. V equals F lambda. We can do that. We can solve for F. So F equals V divided by lambda. So for this problem, our velocity in air up here is 340 meters per second. We divide by 0.2, because we need to change centimeters to meters. So 340 divided by 0.2 is about 1,700 hertz. So 1,700 hertz, right? Okay. Hey, I forgot one thing. It's probably why I had that look on my face. Which harmonic is this? It's a lot easier for open tubes and for strings because you just count the number of loops, and that's your harmonic. For closed tubes, it's a little bit harder because you have this fraction. You're going to have a fraction with these closed tubes, and so everyone's like, well, which harmonic is this? Now, first of all, I'm going to need a little bit of room here. The first thing to know is with closed tubes is they don't go in even numbers. You have your first, then you go to your third, then your 5th, then your 7th, then your 9th, then your 11th. That's how closed tubes work. Whereas open tubes go 1, 2, 3, 4, 5, 6, 7. So that's kind of an issue here. So which harmonic is this? And there's a couple ways in which you can pull this off. Ways in which I do it. Okay, we were, what, 4.5 loops here? We counted 1, 2, 3, 4.5 loops. And then how many waves was that? 1, 2, and a quarter. So it was 2 1/4 waves, right? Now you can use both of those fractions to tell you which harmonic this is if it's a closed tube. And here's how I was taught. 2 times 4 is 8 plus 1 is 9. Here, this does the same thing. 4 times 2 is 8 plus 1 is 9, right? So this is the 9th harmonic. That's a quick and dirty way to do this. The other way you could do it, if you're doing Quest or something, is Google closed tube harmonics, and then you just need to find the one that has the same pattern, and that'll also do it. But that's I think that's a pretty quick way to figure this out. All right. Hey guys, here's a little practice problem. We would have done something like this in class. This is a big plastic graduated cylinder like you have in chem. And then there's a little tube, plastic tube. And this is water. I didn't have a blue marker. So that's water. And so what happens is you're going to strike a tuning fork, which has a particular frequency, and then aim it into this tube. And then you can move the tube up and down, and you would hear at some point you hear a much bigger, brighter sound. A beautiful sound. And this is something called resonance. And so the question is, what length of tube would you need? So how much would you have to raise this little tube up out of the water in order to have resonance at the first harmonic? This little tube inside here is going to be a closed tube because the sound waves would travel down that small tube. When they get to that water, they're going to bounce backwards. So this is a closed tube. All right, pause it. See if you can figure this out. Pause it. All right, well, maybe you pause it, maybe not. Here's how it would work. First thing I can do. I can use this equation. Okay, I know the speed of sound is 340. The problem told me. I know my frequency is 256, and I can solve for lambda. If you do the math, and I've got it in front of me, I'm cheating. Lambda is 1.32 meters. That's the length of your wave. Now it's a closed tube. Okay, this is the second part of the problem. It's a closed tube. All right. It's going to be the first harmonic. So for the first harmonic, that's what the math is for the first harmonic. And this is in the Canvas module, and this is online. If you just Google this, first harmonic, it's just a quarter of a wave, that first picture. Okay, if you look at my first lecture, you'll see it. So I'm going to take 1/4 of the lambda that I got, and the length of the tube that I would need, 1/4 of that's about 0.3. So there you go. There's a nice little problem. The AP test does like to do stuff like this, although I don't think it's on this year, is it? Ha! Okay, there you go.